Hey everyone, welcome back and let's write some more neat code. So today let's solve diameter of binary tree. We're given the root of a binary tree and we want to return the length of the diameter of the tree, which is defined as being the longest path from a particular node. So in this case, it would basically be the longest path on the left side, which could either be this part or this part. Both of those are of length 2. I'm getting that calculation because 2 is the number of edges on that side for the longest path. On the right side, we just have one edge, so that's 1. So the diameter through the root would be 2 plus 1, which is 3. But keep in mind that the longest path might not necessarily run through the root. So let's look at a counterexample. With this tree, if we try to calculate the diameter through the root, on the left side we have nothing, so that's a 0. On the right side we have 3, that's the longest path. You could take multiple different paths, but all of them are going to be of length 3, so the diameter from here is 3. But consider the node over here. Length on the left side is 2, and length on the right side is 2. So total is 4. That's the diameter of this tree. Now, I want to mention to you that this problem is actually closer to a medium problem than an easy problem. Why exactly is that? Because the solution initially seems pretty obvious, right? To get the result, we can just try to calculate the diameter through every single node in the tree. How do you do that? Well, just like I did, get the longest path on the left and the longest path on the right and add them together, aka sort of like the height on the left side and the height on the right side. Generally, we do this recursively with some kind of DFS algorithm, but the tricky part about this problem is that the return value, obviously, of this DFS is going to be the height. So what we want to return from this right subtree up to this node is, of course, the height. But that's not the result that we're ultimately trying to compute. What we're actually trying to compute is the diameter. Now, in terms of the code, there are multiple ways of handling that. The way I'll show you is sort of by using a member variable, or you can even think of it as sort of a global variable with respect to the recursive function. But the algorithm will be exactly like this. Recursively run DFS. From the left subtree, we reach null. So the height of that, of course, is going to be 0. That's what we return up here. Then do the same on the right side. And then we'd continuously go down. And so here, we'd reach the case with just a node. The height of that, we will say, is going to be 1. That's going to be returned up to the parent, and that's basically saying that the length of this is 1. Same thing for this side, we'll say the length is 1. So now when we want to compute the diameter from here, we're going to maintain a global variable, which I'll call it the result, or this for short. And initially we'll set it to 0. This is what we're trying to maximize, of course. And from this node, we calculate a diameter of 1 plus 1, which of course is going to be 2 now. That's the biggest result that we have. Now, from this node, I want to return up to my parent the height of this tree. So what do I do? Well, the height is different than the diameter, so we actually will take the max of the left subtree, the max of the right subtree, and add 1 to it. Well, in this case, they're the same, so we just get 1 and then add 1 to it, which is this edge. So we'll say that the height here is going to be 2. Obviously, it didn't have to be like that. Suppose there was a node over here, and then maybe the height of this right tree would have been 2, and then we would have returned 2 plus 1, which would have been 3. So that's generally the core idea. We would do the same thing from here because it's kind of symmetrical to this side. So this would be 1 and 1. And then the height of this is 2. Height of this is 2. 2. Those are going to be returned up to 3. Add them together. The diameter now is going to be 4. It's going to be increased all the way up to 4. From here, we want to take the max of left, max of right, it's 2, and we want to add 1 to it because of this edge here. So then we say the height of this part is 3. We return that up to the root. I'll make it another color, 3. Root is going to do the same thing. Take left plus right, add them together, we get 3. This time it's not greater than the result. So our result will stay unchanged and it will be 4. 4 is ultimately what we would return. But it's not going to be returned from the recursive function. Keep that in mind. We're going to have a separate variable that's sort of going to be global, which does that. And since we were able to accomplish this by just visiting each node once, we will say that the time complexity is linear and the space complexity is going to be proportional to the height of the tree, which could be log n for a balanced tree or n for a non-balanced tree. So we're going to solve this recursively, and I like to do it with nested functions. So I'm going to have my DFS here, and I'm going to pass in a single variable cur. Remember that this DFS is not returning the diameter, it's going to return the height. That's the most important thing about this problem. It's not a trivial recursive problem. The base case, though, is going to be pretty easy, if not cur. Therefore, we reached a null node. The height of that is, of course, just going to be 0, so that's what we return. Otherwise, let's do the recursive case. Let's get the height of the left subtree. Let's call DFS on cur.left. Let's do the exact same thing for the right subtree, just like this. Now, remember, there's two things we want to do.
I
We
have
want to
no
potentially
idea.
update the result, and we want to return the height of the tree from cur. So let's start with the result. I'm going to create a variable self.result is equal to 0. This is basically making it a member variable of this class, like an instance of this class, so that it is accessible inside of this nested function. So when I want to maximize the result, I'm going to set it equal to the max of itself, self.result, and the current diameter. How do we get that? We'll just take the left and right and add them together, just as we did in the drawing explanation. Now for returning, we're not returning this. We're not returning the diameter. Remember, this returns the height. How do we calculate the height, though? Well, it's either going to be the max
I know.
of the left or the max of the right. And also, don't forget to add 1 for the current node that we are at. This just tells us the max of either of the subtrees, but plus 1 will give us the max of the height from cur. Now, that's actually pretty much it. It's not easy to come up with. Remember, the complexity of this comes from the fact that the return value is not the result. So down here, we're going to return self.result, but don't forget, don't be like me and forget to actually call the recursive function starting from the root. This is the entire solution. You can see that it works and it's very efficient. I just want to show you a couple different ways that you could have handled this global case, though, at least in Python. Another way is just making it a local variable result, and then in here to update it, let's get rid of all the self dots here. Let's get rid of that, and let's get rid of that. To update result, you have to kind of declare it non-local first. You want to say that this is not a local variable to this function. It's actually the same result that was declared out there. So this will do the same thing. So if we execute this, you'll see that once again it works. It says it's more efficient, but LeetCode runtimes are random, so don't really pay attention to that. We'll do the same thing. Update it. Let's get rid of returning this. We're not returning
So, Congress. Let's do it from there.
turning that come up with, remember the
Maximum
complexity of this
maintenance. Max.
comes from the fact that you can see that it works. We're going to return
No. Someone you need to go now. Hey! Okay, fine. I'm gonna need to see.
function starting
Oh my, the heck?
Spectre Gadget. Du-du-du-du. Woo-hoo.
from the root. This is the entire solution. You can see that
Okay.